Hello friends, welcome back to the online certification course on watershed hydrology. I am Rajendra Singh, professor in the Department of Agriculture and Food Engineering at Indian Institute of Technology, Kharagpur. We are in module 2. This is lecture 4 and the topic is infiltration part 1. In this lecture, we will define and describe the infiltration process. Then we will go for infiltration measurement. We will talk about infiltration indices and also infiltration estimation using various mathematical models. Coming to defining infiltration, it is the movement of water through the soil surface into the soil profile, and it is the most important abstraction. We have already discussed various types of abstractions, and while defining or classifying abstractions also, I mentioned that infiltration is the most important abstraction. And if you remember, when we discussed about the hydrological cycle, and then also we said that when evaporation or transpiration occurs, then cloud formation takes place, finally condensation occurs and precipitation occurs. The precipitated water, when reaches the soil surface, the very first process which starts is infiltration, and that is what we are discussing today. Infiltration, the very first process which starts, and it affects the amount and time distribution of rainfall excess available for runoff and surface storage during a storm. And we discussed this also, that once precipitation reaches the earth's surface, the first thing it has to do is to satisfy the infiltration capacity of the soil. So, obviously, if the infiltration capacity of the soil is more, less water will be available for other processes, or rather than the next process is overland flow, as we discussed in hydrological cycle. So, obviously, the amount of runoff or the amount of storage, because we know that when overland flow takes place, when flow starts in the form of a sheet, then if there are potholes, then water gets stored there. So, both the runoff and the surface storage will depend on the infiltration, because rainfall excess, if you remember, we also said that the total precipitation minus losses, we call that rainfall excess, and that is the part of precipitation or rainfall which is available for overland flow and other processes. Infiltration plays a significant role in the runoff process by affecting the timing, distribution and magnitude of surface runoff. So, just now we discussed that once precipitation satisfies the infiltration capacity, then only overland flow or surface runoff starts, and of course, the timing will be affected. So, will be a distribution, because the infiltration capacity of the soil along the way, along the path will keep on changing, and as and when it changes, it will affect the runoff magnitude as well as its distribution also. The accurate estimation of infiltration helps determine surface runoff, subsurface flow and storage of water within the watershed. So, just now we saw that obviously once infiltration is known, we know how much water is available for overland flow, and of course, if we know the superficial dispersion, etc., we know how much water could be stored. Also, because once the water infiltrates, then there are two possibilities. One is that it flows, if the soil profile or the profile is such, then it starts flowing parallel to the surface, or it joins the groundwater level. So, if groundwater level is here, so groundwater, if its level is there, then it may join that. So, either it will affect the subsurface flow or the groundwater flow. So, it all depends on the infiltration magnitude. Coming to infiltration process, it all starts, as we discussed, once rainfall or snow contacts the soil surface. So, whenever rainfall occurs or snowfall occurs, then only infiltration process starts. Then when that happens, water is driven into the porous soil by the force of gravity and the capillary attraction of the soil pores. So, as you can see here, when the flow, when the precipitation occurs or snowfall occurs, there will be water coming into the contact of soil surface. Then of course, depending upon the magnitude of rainfall, depending upon the head that is generated on the surface, the gravitational, through gravity, the water will start getting into, and also the capillary forces also will act. The first, the water wets the soil grains by forming a hydrogen bond with mineral surfaces. So that is what is happens here. As you can see that the soil grains or the chemicals or particles which are there in the soil, they will be attracting this water, and then a hydrogen bond will be formed. And the adhesive forces attracting two unlike molecules of water and soil material also act in concert with capillary surface tension forces. So, we already saw that there is a force of gravity, we also saw there is a capillary attraction, but in addition to these two, adhesive forces also come into picture, because there will be when two unlike molecules, that is of water and the soil particles, they come in contact, they will attract each other. So, because of that, adhesive forces will also act. Now, as more water enters the soil, that means if the precipitation continues, these forces cause the water to penetrate openings in the soil surface and migrate downward, with numerous menisci forming at the interfaces between air and water. So, as you can visualize that, where if more and more water comes, because of capillary forces, more and more water will be entering the soil surface, and obviously it will be filling the soil pores, but because there are pocket holes of air or air holes also, so there might be some spaces where air still remains in the beginning. And with more water entering into the soil, the menisci are destroyed, then the force of gravity takes over and moves the water down towards the water table. So, obviously, if this flow process continues, then menisci will disappear, and of course, the water will start moving downwards because of the gravitational force, and it will percolate down to the water table. When the supply of water to the soil, that is rain, stops, the water percolates or moves down by gravity until the menisci begins to reappear, and the forces of surface tension begin to dominate again, holding water in the pore. So, obviously, when the rainfall stops, the reverse process starts taking place, and as a result, what happens that as long as there is enough water is there, gravity will take the water down, but once supply is not there, the gravitational forces will reduce, and it will be the surface tension or capillary forces will take over, and obviously, because of the surface tension, the menisci will start reappearing again. So, that means the entire reverse process, and the soil will go back to its natural condition where it was before the rainfall started. Now, this figure shows the soil water distribution profile during the infiltration process for homogeneous soil under ponded conditions. So, this assumes that the soil here is homogeneous, and there is a ponded water surface on the soil, on the ground. So, what happens in this such a case, during the infiltration process, 4 distinct zones may be identified, and these zones are saturated zone, which extends only to a depth of few millimeters. So, this is where it is taking place, and this is basically we are seeing the soil water distribution profile. So, on the top there is a saturation, because there is a ponding water, and then of course, the saturation zone which extends only to a few depth of millimeters, that is this part here, again because it is saturated zone, it is direct contact. So, obviously, this is also saturated. Then comes the transition zone, where there is a rapid decrease in water content with depth. So, just below the saturation zone, there is a transition zone, where you can see that there is a sharp decrease in the water content. The third is transmission zone, where water content does not change appreciably with depth. So, obviously, as you can see here, this particular zone, this transmission zone, that is which takes the water further downwards, there it is for much larger depth, and also as you can see that almost constant moisture content is almost constant if in the entire profile. And lastly, there is a wetting zone where there is a sharp decrease in water content with depth. Again you can see here, this is the wetting zone, this portion, and of course the lower boundary condition, the lower boundary of the water penetration, that is referred to as wetting front. So, of course, on the surface, on the top there is a ponded water, on the bottom there is a water wetting front, and of course in between there is a saturated zone, transition zone, transmission zone and wetting zone. So, all these zones can be distinctly identified in a soil profile. Coming to infiltration process, the rate at which water enters the soil at its surface is defined as the infiltration rate. So, rate we already saw that infiltration is the entry of water through the soil surface, and the rate at which it enters the soil, that is infiltration rate. And infiltration rate is a function of time defines the infiltration curve. So, this is what we are seeing here, that is nothing but infiltration curve, that is infiltration rate against time. If we plot, this is the kind of curve we will get, and that is the infiltration curve. Under most conditions, the greatest rate of infiltration occurs when water first contacts into soil surface, that means when the soil is completely dry and when the capillary forces are strongest. So, that means when the soil is dry, the capillary forces are strong, and when the water comes into contact, and because of that always you will find that infiltration starts at a very high rate. But as you can see that it gradually reduces, and that happens is that water penetrates the soil to some depth, the resistance to forces acting on the water increases and the rate of infiltration decreases. As a result, a fairly constant rate of infiltration is attained after some time has passed. So, if you see here, it starts at a very high rate and then it starts decreasing, and then if the infiltration experiment is continued for longer period of time, then it becomes almost constant, as you can see here. So, here F0, which is here, that is the initial infiltration capacity rate, and Fc, which is the constant infiltration capacity rate if the infiltration experiment or infiltration continues for a longer period of time. When the availability of water, which is the case when water is ponded on the surface, is not a limiting factor, then where there is a ponding water supply for a time, then the maximum rate of infiltration at any time is called the infiltration capacity of the soil, and this was defined by Horton in 1933. So, when water is pounded on the surface, obviously then that assumes that there is a continuous supply of water, then water is not a limiting factor, and it is the capacity of the soil, infiltration capacity of soil, that determines how the infiltration rate will change. So, that is why that the infiltration rate is the infiltration capacity of the soil. And infiltration capacity asymptotically approaches a constant value after a certain period of time has passed, and is called the constant infiltration capacity Fc, which is here, as you can see here. And typically this value is almost equal to Ks, which is saturated hydraulic conductivity of the soil. So, if you continue the experimentation, then obviously the constant infiltration capacity rate will be attained, which is Fc, and which is almost equal to saturated hydraulic conductivity. One important thing is here that when it is a ponded condition, then it is F is called infiltration capacity rate. If it is a rainfall where there is no ponded condition, that is water this condition that water is not a limiting factor, that does not hold good, then it is called simple infiltration rate. So, infiltration rate or infiltration capacity rate, that nature of the curve will remain the same. Only thing is that the terminology we use in case of ponded condition, we say it is capacity rate. In the case of rainfall, we call it infiltration rate. Now, we come to infiltration measurement, and typically infiltration is measured by equipment called ring infiltrometers, and typically we use what we call the double ring infiltrometer, which is also called as flooding type infiltrometer, that is used for measuring instrument. Double ring because it has two concentric cylinders, as you can see here. The inner cylinder has a diameter, there are two, so this is the inner cylinder, this is the outer cylinder. The inner cylinder has a diameter of 300 millimeters, whereas the outer cylinder has 500 millimeters diameter. So, diameter 300 and 500, that is standard, and of course, for conducting experiment we really put them into the soil, and up to certain level they are put they are sunk into the soil basically, and then the measurement is done. And when the in situ measurement is done, then basically we maintain a depth of 60 to 800 millimeters in both the cylinders, that is both the inner and outer. So, while doing the experimentation, the water level here and here at both places it is maintained in between 60 to 1600 millimeters. And the outer cylinder basically is used as a buffer to check lateral flow of water. So, actually infiltration measurement is done in the inner cylinder, that is this is used for measurement, wherein this outer cylinder is used for creating the buffer, and that buffer is basically to check the lateral flow of water, because as we have seen that infiltration means it is the water entry from the soil surface, and typically that has to be vertical. So, in order to avoid the lateral flow of water and keep the water moving vertically, we use this outer cylinder. And the water level fall in the inner cylinder with time is measured using a hook gauge and water refill to maintain the depth. So, when the infiltration measurement starts, we maintain the requisite or pre-decided water level, say 100 millimeters, and as the time passes, as the infiltration starts taking place, of course, there will be fall in the water level. So, that fall in the water level is recorded using any kind of measuring device. It could be a hook gauge, which could be used to measure the changes in the level, and that is recorded with time. So, time and the change in the water level in the inner cylinder, that is recorded, and water is refilled to its original level, and that is how we continue the experiments. And then with time we of course we know and we can plot this curve f versus time, and this is the curve we normally get. But this measurement should continue until the infiltrator volume is constant over a period of 1 to 2 hours. This is important because if we remember that we said that it starts at a high rate and then it decreases and attains a constant. So, in order to get this constant value, we must continue this experimentation for a longer period of time, and unless and until the infiltration volume is constant over a period of 1 to 2 hours. So, when it remains constant for significant period of time, we stop the experimentation. And the main disadvantage of this infiltrometer is raindrop impact effect is not simulated. Before that, this picture shows the double ring infiltrometer with an automated Marriott reservoir, and this Marriott reservoir does nothing but maintains a constant water level in the inner cylinder. We, as I mentioned, that we use a hook gauge to measure the water level fall and then refill the inner cylinder. But if you use the Marriott reservoir, then automatically the water level is maintained, and through the cylinder we know how much water has infiltrated. So, you do not have to really calculate, you automatically get that value. But what happens is that raindrop impact, when if you have read soil erosion, you know that when raindrop impacts the soil surface, what happens that there is a splash, and because of that splash the soil particles are, they are loosened, and as a result what happens, the water becomes dirty, number one, and also after certain period of time the surface gets sealed, and because of the surface sealing effect the infiltration rate is expected to be lower. But because in the case of double ring infiltrometer, the raindrop impact is missing, and we always have a clean water and a sufficient head build up, that is why typically it gives a higher rate of infiltration. Then in order to take care, there has been a device called rainfall simulator infiltrometer that has been developed, which simulates the raindrop impact effect. So, that of course, there is a drop forming mechanism and water is maintained here, and then constant head is maintained here basically. There is a pressure head regulator for maintaining constant head, and then there is a drop forming mechanism. So, under constant head, these raindrops are formed and they fall on the soil surface. So, that process of the rainfall is simulated in this case. So, since infiltration depends on properties of soil through which water must infiltrate and the properties of water to be filtered, raindrop impact effect, which changes the property of both soil and water, is certain to be important factor affecting the infiltration process. So, that means the water gets dirty, also the surface sealing effect takes place because of the simulation of the raindrop impact. And that is why infiltration rate is lower than that measured by a ring infiltrometer, because the surface sealing and the dirty water is there in this case. So, obviously, it gives a more reasonable value of infiltration compared to a ring infiltrometer, which gives a higher value of infiltration, as I already mentioned. And besides measuring infiltration, this such a rainfall simulator infiltrometer, it can also be used for runoff and soil erosion studies. So, we can also estimate how much runoff will take place if a certain intensity of rainfall is maintained and how much soil erosion will take place. So, that gives us a additional advantage in this case. Now, we come to infiltration indices, and there are two types of indices which are used, the phi index and the W index. The first one is a phi index, which is the average rainfall rate above which the rainfall volume is equal to the runoff volume. Basically, phi index or the indices are used to represent the average loss. As we saw that the abstractions are loss, nothing but loss. So, basically, because the different abstractions will change with the location, with the conditions within a particular basin itself. So, that is why, and it is very difficult to estimate each one of them. So, that is why the concept of this average loss has been brought into picture, and that is what phi index does. The phi index is the average rainfall rate above which the rainfall volume is equal to runoff volume. So, that simply means that you see this is a hydrograph, you can see here. So, hydrograph, you remember we plot rainfall intensity with time here. So, this is time here. So, rainfall intensity versus time. So, obviously, when rainfall occurs, there will be some initial losses, and of course, after satisfying the initial losses, infiltration will start, but at the same time the runoff, the overland flow will start, but at the same time infiltration will also continue. So, this is the entire process. So, if we consider this as phi index, that is the phi index, if we draw a line of phi index representing the average losses over the basin, then obviously whatever area of the curve is under hydrograph is above phi index line, that represents the runoff volume. So, that is how if we find out, we can find out what is the total runoff volume. So, if we measure the total runoff volume, the phi index can be calculated from rainfall hydrograph as phi equals to P minus Q by TD, where P is the total precipitation, Q is the total storm runoff, and TD is the duration of the rainfall excess. That is, the rainfall excess is this period, that is where the precipitation is greater than the losses, and losses here are being represented by phi index, and F here is the cumulative infiltration. So, obviously, there are initial losses, and of course, when the overland flow occurs, then also infiltration process continues. So, this is what this picture shows here, and these initial losses are also considered as infiltration in case of phi index, as we can see. So, that is why there is another index that has been brought into picture, that is W index. The initial losses may be separated from the overall abstraction to improve the phi index, and then the average infiltration rate is referred to as W index. So, W index, as you can see here, there is a change with the phi index, that IA, that is initial abstraction, is taken into consideration by calculating the value of W index, and that is why this W index is likely to be slightly lower than the phi index value, because here the initial losses have been taken into account. Let us take an example, that is example 1. The following figure presents the hydrograph for a 3-hour storm. The surface runoff for an event is estimated to be 38 mm. Determine the phi index for the event. So, we have a rainfall hydrograph given at 30 minutes interval, and it entire continues for 160 minutes, that means 3 hours, and these are the at every 30 interval, these are the rainfall intensity, and of course, and this question is taken from GATE examination 2011. So, of course, from the figure we can tabulate the rainfall intensity and cumulative rainfall as given here. So, different times 0 to 30, we know the intensity of rainfall, that is 0 to 30 it is 10, then 30, then 40, 50, 25 and 8, and the rainfall during the period obviously we can find out, because we know that this intensity of rainfall is millimeter per hour and it is half an hour. So, that means 50% of that is rainfall during the period. So, 5, 15, 20, 25, 20, 12.5 and 4, and the total rainfall comes out to be 81.5 millimeters. Now, so the surface runoff already given is 38 mm, and total rainfall during event we found out is 81.5 mm. So, and the duration of rainfall excess is 3 hours. So, we can calculate the first approximation of phi indexes P minus Q by TD, and that value comes out to be 14.5 millimeter per hour. Now, if we say 14.5 millimeter per hour, that means this is where somewhere this phi index value we will plot. But remember the figure, we said that only the precipitation which is lying above this phi index line, that is the effective rainfall, and that is where the runoff will be generated. Now, if phi index is 14.5 mm, there will be no excess rainfall during 0 to 30 millimeters, as you can see here. This is lower than phi index value, and also here 150 to 180, which is lower than phi index value. That simply means that we have to reassess the total depth by excluding these durations. These durations do not contribute to effective rainfall. So, that simply means that if we neglect this and this, then total rainfall value comes out to be 72.5 mm. And now, with known values of Q, and our time also now reduces to 2 hours, because we have taken 1 hour, half an hour on either side away. So, that means the new estimation of phi index value comes out to be 17.25 millimeter per hour. And if you look at the value here 17.5, so that means somewhere it will be somewhere here. So, obviously, we have only considered this portion as effective rainfall. So, that remains good. And so, since the estimated phi index is less than the rainfall index during 30 to 150 minutes, the rainfall in excess of phi index will go as direct runoff. Thus, the phi index of the event is 17.25 millimeter per hour. We can take another example quickly, that is the observed rainfall of a 12-hour duration event is given the table below. If the phi index of the storm is 4.6 millimeter per hour, determine the total direct runoff of event. So, cumulative rainfall is given and different times, and this question is from GATE 2016. So, same process will be rainfall during the 2-hour interval and intensity will find out. So, that means basically we need the hydrograph, and the phi index value is given 4.6. So, same principle, when the intensity of rainfall is lower than phi index, then there will be rainfall intensity above the phi index will be direct runoff, there will be no runoff produced. So, that means direct runoff is 0, 0, 0, 0 here, and 5.4, 10.4 and 15.4. That means this value minus this value will be the direct runoff millimeter per hour, and because this 2 hours interval we are talking about, so obviously it will be double of that is direct runoff depth. So total direct runoff depth comes out to be 62.4. So total direct runoff during the event will be 62.4 millimeters. Now we come to estimating infiltration using mathematical models, and usually infiltration models are classified as empirical, semi-empirical and physically based, and these are the different models under different categories. Empirical models, we have Kostiakov equation developed in 1932, modified Kostiakov by Smith in 1972, semi-empirical models Horton 1939-1940, and under physically based we have 3 different models, Greenham given in 1911, Philip in 1959, 57 and 1969, and the third one is Richard's equation in 1931. We will see these in remainder of today's lecture and the next lecture. Starting with Kostiakov model. Kostiakov model expresses cumulative infiltration capacity in this form: F equals to A to the power T AT to the power B, where A and B are empirical parameters with A greater than 0 and B between 0 and 1. And infiltration capacity rate, this is cumulative infiltration capital F. The rate can be expressed by differentiating above equation with the condition that F equal to 0 at T equals to 0, that is F A B T to the power B minus 1, and this is the infiltration rate, this is rate, and this is cumulative infiltration. Modified Kostiakov model is just an modification. Here you can see that after attaining FC also infiltration will continue, that part is taken into account. So capital F, that is cumulative infiltration, is ATB, similar to Kostiakov model, plus FCT is also there, and infiltration capacity rate is again if you given by equation number 4, that comes by differentiating equation number 3. We will take a quickly an equation, a problem. An infiltration rate of water in a 30 by 30 meter filled strip is found to follow Kostiakov equation with A equal to 0.45 and B equals to 0.65. If the infiltration rate is in millimeter per hour and time is in minutes, determine the infiltration depth in 45 minutes period. So Kostiakov equation we already know, I equals to AB T to the power B minus 1. We are given A, we are given B. So I in terms of T we can find out, which comes out to be I equals to 0.2925 T to the power minus 35, where I is in millimeter per hour and T in minutes. So at 44 we want to get up, so we can integrating the equation with reference to T, because we want cumulative infiltration. So we will get I equals to, or capital F we have said in the previous equation, 0.45 T to the power 0.65. So for T equal to 45, we get a value of 5.34. So for the field strip, infiltration depth in 45 minutes is 5.34 millimeters. So with this we come to the end of this lecture. Thank you very much. Please give your feedback and also raise your doubts so that can be answered on the forum. Thank you.